right, so this lesson is on counting, um, and we're going to actually start with the first 5 rules that were given on your counting handout. All right, so counting is literally about counting. It's about counting the number of ways an events can occur, maybe counting how many ways I can choose 2 students from the class of 13, etc. So it's literally about counting, but it's about finding ways to count quickly as opposed to 1, 2, 3, 4, right? But actually doing calculations to help us to count without doing all the work and that would involve counting one by one. All right. So using the handout, we're actually going to start with rule number 2, and then I'll go to rule number 1. Rule number 2, which is the addition theorem or the addition principle, says if a total event can be accomplished in 2 or more mutually exclusive alternative ways, then the number of ways in which the total event can be accomplished is given by the sum of the number of ways in which each alternative event can be accomplished. Very wordy, but it's actually very easy. The key thing here to pick up is the word or, mutually exclusive, and sum. So if the events that you're looking for, if you're doing an or situation, if the question is about the number of ways of doing this or that, right? And those 2 events are mutually exclusive. There's no overlap, there's no intersection. Then all you have to do is to add up the number of ways of doing each. All right, so let's look at an example. As I said, it's quite simple. Ray owns 5 bicycles and 3 cars. He can get to work using any one of these vehicles. In how many different ways can he get to work? So this is an or situation. So he has 5 bicycles, 3 cars, and he wants to use one of them to get to work. So it's either he's going to be using one of the bicycles or one of the cars. So it's a simple calculation. Number of ways would be equal to adding the 5 and the 3 because he has 5 bicycles and 3 cars. And it's one of them that you're using. It's one of the bicycles or one of the cars. It's not an and situation. So this is 8. Right? So there are 8 different ways that he can get to work. And that's rule number 2. Nice and simple, straightforward. Rule number 1 now, which is the multiplication theorem or principle, says if one event has m possible outcomes and a second independent event has n possible outcomes, then there are m times n total possible outcomes for the 2 events together. So this one is about multiplying. The first one was about adding for an or situation. This one is multiplying for an and situation, right? We multiply. So back to Ray. Ray owns 5 bicycles, 3 cars. He plans to ride a bicycle to and from work and then take one of his cars to go to a restaurant for dinner. In how many different ways can he do this? So this is an and situation because he needs to choose a bicycle to go to and from work, and then he needs to choose a car to go to a restaurant. So that's an and. Choosing a bicycle and then choosing a car. So the number of ways in this case would be equal to 5 times 3, which is 15, as opposed to the 5 plus 3 where he was choosing a bicycle or a car. This time he's choosing a bicycle and a car. So we multiply. Now we move on to rule number 3. In this, well, the subtopic for what we're about to begin is permutations and combinations. We're starting though with permutations. Another word for permutations, by the way, is arrangements, the number of ways of arranging some objects. All right, so rule number 3, the number of ways of arranging n distinct objects in a line is n factorial. Now, factorial has not been introduced to you yet, but it's quite simple. Let's say we have 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. So we start with the 5 and then we're going down by 1 each time and multiplying. 4 factorial would be 4 times 3 times 2 times 1, all the way down to 1. And so n factorial would be n times n take away 1 times n take away 2, etc., all the way down to times 2 times 1, depending on the value of n. So if you have 3 distinct objects, let's say we have A, B, C. Those are the letters that we have. Those are our distinct objects. We have A, we have B, we have C. And we want to arrange them in a line. How many different ways can we do that? Let's list them and see. So you have A, B, C, A, C, B, sorry, B, A, C, B, C, A, C, A, B, C, B, A. 6. 6 different arrangements, right? 6. And we could have calculated it without writing them out. We could have calculated it using n factorial. So we have 3 objects to arrange in a line. That would be 3 factorial, which is 3 times 2 times 1, which is 6. You can also find the factorial symbol on your calculator so that you don't have to do all the work. So you're going to pause this video, look for the exclamation sign. It might be N exclamation or maybe X exclamation. That is what we use to calculate factorial, because when you get some big numbers, for example, 10 factorial, I don't expect you to calculate 10 times 9 times 8 times 7, etc. down to times 1. You would just plug in 10 on your calculator, press the factorial button, press your equal, and that will give you your value. So let's look at an example now of using rule number 3. A witness reported that a car seen speeding away from the scene of a crime had a license plate that began with VRW, he wasn't sure which one, followed by the digits 4, 7, and 8, and then letters ACE. He could not, however, remember the order of the digits or the end letters. How many cars would need to be checked to be sure of including the suspect's car? So basically, we're looking for the number of arrangements of, so it starts with V or W, not sure, followed by 478 in some kind of order, followed by ACE. So we have V or W, then we have 4, 7, 8, some kind of order, and then we have ACE in some kind of order. So we need to work out How many ways of arranging these? Arrangements, when you're working out arrangements, one of the things that might help is thinking about filling in blank spaces. So we have 1, 2, 3, 4, 5, 6, 7 spaces that we need to fill in. 1, 2, 3, 4, 5, 6, 7. 7 spaces that we need to fill in. The first space is going to be filled with VRW. The next 3, 4, 7, 8. The next 3, ACE. The ACE and the 4, 7, 8, we need to arrange those, right? So for the first slot, I'm going to say number of ways to choose first letter would be 2. We have 2 choices for that first slot. The person know they saw a V or a W. They weren't sure which one. So we have 2 choices that we'll have to check. Those license plates starting with V's and those starting with W's. And then for the next 3 slots, we have to arrange the 4, 7, 8. It's a number of ways to arrange 4, 7, 8. And we would be using rule number 3 for this one. It would be 3 factorial, right? The number of ways of arranging n distinct objects. And I didn't stress on it, but distinct is important. It has to be different objects. So it would be n factorial. So in this case, 3 factorial, right? Because it's 4, 7, 8. 3 objects, 3 numbers. And then lastly, we have the ACE to arrange. And that would be 3 factorial as well. 3 letters, 3 distinct objects, 3 factorial. So the total number of license plates equals, and we would multiply, and we'd multiply because it's not an or situation, it's an and. We have 2 choices for the first letter, and then these 3 choices, 3 choices for the next 3, and then, well, technically it's not 3 choices, 6 choices. It's 3 factorial, so it's 6, right? So 6 ways for the next 3, and then 6 ways for the next 3. So we're actually multiplying 2 6s, 12, 12 times 6, 72. So there are 72 different license plates that we would have to check to ensure that we include the suspect's car. Now we look at rules number 4 and 5. The number of ways of arranging in a line n objects of which p are alike is n factorial over p factorial. So this time we're not dealing with distinct objects. We have some of them that may be alike. So for example, if you have, instead of ABC, we had AAB. It's not going to be 3 factorial ways now of arranging them. Let's see how many arrangements we would have. So of course we would have the AAB, we would have ABA, we would have BAA, and that is it. Can't think of another one. So AAB, ABA, BAA. So we have only 3 arrangements this time, as opposed to the 6 when we had ABC that were distinct objects. Now because we have A's, 2 A's, the number of arrangements has decreased. So we could have calculated it using n factorial over p factorial. So that would have been 3 factorial, because we have 3 objects, divided though by 2 factorial, because 2 of them are alike. So we divide by 2 factorial. That's 6 divided by 2, which gives 3, just like we worked it out to be, right? So 3 different ways of arranging 3 objects in a line where 2 of them are alike. Now we can extend this, right? If you look at rule number 5 is just extending rule number 4. The number of ways of arranging in a line n objects of which P are alike, of one type are alike, Q of a second type are alike, R of a third type are alike, and so on, is. So we had P of them of, P of one type being alike, so we divide by that P factorial, just like in 4. But we may have another type that several of them are alike, so we divide by that factorial, and so on. So that would be a case like, let's say, A, B, C, C, for argument's sake. Right? So here, I'm not going to write out all the different arrangements, but we can calculate how many arrangements there would be. We have 1, 2, 3, 4, 5, 6 letters. So that's 6 factorial. Divided by, we have 2 A's, so 2 are alike. We only have 1 B, so we're okay with that. But we have 3 C's. So we also need to divide by 3 factorial. And we would calculate that and get 60. All right, so let's look at some examples now of using those 2 rules, rule number 5 and 4. In how many ways can the letters of the word statistics be arranged? So we have, let's count the number of objects we're dealing with. 1, let me write it out. 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 objects dealing with. 10 objects, so it's going to be 10 factorial. However, there are some that are repeated, some are alike. So we have 1, 2, 3 S's, so we need to divide by 3 factorial. We have 1, 2, 3 T's, so divide by 3 factorial. 1A, 2 I's, so we divide by 2 factorial. 1C, and that's it. And then we turn to our calculators and we should get a value of 50,400. Another example, if the letters of the word minimum are arranged in a line at random, what is the probability that the arrangement begins with MMM? So here now we're tying in probability with our counting. We did probability already, so we should be able to tackle this question. So let's look at it. We're looking at the word minimum, arranging it in a line, and we want the probability that the arrangement begins with MMM. Now, for the probability type questions, I suggest working out the number in your sample space first. So looking at the arrangements without any special conditions, without looking at any particular event, just working out the number of arrangements to begin with. So for the number in our sample space, it's going to be, let's count the letters that we're working with. 1, 2, 3, 4, 5, 6, 7. So we have 7 letters that we're working with. So that's 7 factorial, but some of them are alike, so we need to work that out. We have 3 M's, so we divide by 3 factorial. We have 2 I's, so we divide by 2 factorial. And I think that's it for the repeated ones. All right. So 420 is the number of ways of arranging the letters in the word minimum. But we're looking for a particular event now. They want us to find the probability of a particular event. So let's define our event. I'm going to use A to define the event. Arrangement begins with M, M, M. So again, remember, you can treat this like filling in slots or blank spaces. So we have 7 spaces to fill. We want our arrangement to begin with MMM. There's only one way of doing that. Placing the MMM right there. So we want the arrangement. Well, rather you place what it is that you want and then you work out the rest. Let's put it that way. So we want our arrangement to begin with MMM. So we place the MMM in those first 3 slots, which means all we need to figure out now are the number of ways of arranging the remaining 4 letters. The remaining 4 letters we have are I, N, I, U. All right, so we have those 4 to fill in that slot. So in other words, working out the number of ways of arranging those 4. And that would be 4 letters, so 4 factorial divided by 2 of them are alike, 2 factorial, and that's going to give me 12. And that represents your NA, right? The number in A, which means the probability of A, the probability that your arrangement begins with MMM is going to be 12 divided by 420, which is 1 over 35. All right, next example. 10 students are placed at random in a line. What is the probability that the 2 youngest students are separated? 10 students. We want to keep the 2 youngest students separated. In other words, we don't want them together. For these types of questions, it's better to work them being together, and then we'll do some subtraction to figure out the apart or the separated. So if you get a question that is asking you about keeping, some objects together, you work it as together. If you get a question asking you to keep some objects separated, you still work it as together, and then you have an extra step, right? So we're going to work it as keeping the 2 youngest students together. And then, of course, the opposite of that would be not together or separated. All right. Again, it's a probability question. So we want to start off with NS. We want to start off with just a number of arrangements, not any special condition, not keeping the 2 youngest together, simply just the number of ways of arranging these 10 students in a line. And that would be your NS, which is 10 factorial. So 10 factorial ways, and of course, our students are distinct objects. So 10 factorial ways of arranging 10 objects or 10 students in a line. That's NS. Good. Now let's consider keeping the 2 youngest students together. So I'm going to define my event. A as keeping two youngest students together. All right. So let's pretend that these are the two youngest students. What we're going to do is we're going to work out the number of ways. Well, we're going to pretend like these two students are one student or is one student, right? So we're going to treat these two as one, right? One object, and then work out the number of ways of arranging our objects. So instead of having 10 objects to arrange, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 objects to arrange, right? If we keep those two as one, treat those two. So let me write that. Treat two youngest as one, right? It means we have 1, 2, 3, 4, 5, 6, 7, 8, 9. In other words, the remaining 8 plus this one gives you 9, right? So therefore, 9 objects to arrange. And that would be 9 factorial ways of arranging those 9 objects, right? Then we arrange those two students between themselves, right? So here, call this student number 1 and call this student number 2. Apart from having them as 1, 2, we could also have them as 2, 1. So we had the purple shirt person here and then the blue shirt person there. So we have to also work out the number of ways of arranging those two between themselves. So number of ways of arranging the two. Two factorial or just two, right? Good. So total number of ways or total number of arrangements. We're going to multiply 9 factorial times 2. All right, it's an and situation. We arrange those 9 in quotation objects, and then within those arrangements, we're arranging these two. So it's a multiplication situation. So 9 factorial times the 2. And that represents your NA, the number of ways of keeping those two students together. So the probability of A is going to be your 9 factorial times 2 over your 10 factorial. And that gives 1/5. So that is the probability of keeping the two youngest students together. But what we want is the opposite of that. We want keeping them separated, which instead of A would be not A. So we're going to subtract the 1/5 from 1, giving us 4/5. So the probability of keeping the two youngest students separated would be 4/5. And now for the last example. The 6 letters of the word London are each written on a card, and the 6 cards are then shuffled and placed in a line. Calculate the number of different arrangements. So we have London. Part A is easy enough. all we need to do is to calculate the number of ways of arranging these letters. So that would be we count the letters 1, 2, 3, 4, 5, 6. So that's 6 factorial. But some of them are repeated, so we need to do divide by. We have 2 O's, so 2 factorial, and 2 N's, so 2 factorial. 180 different arrangements. B, find the probability that the middle 2 cards both have the letter N on them. It's a probability. We've already worked out the number in the sample space, which is the number of arrangements overall. That's 180. So we can jump straight to the event, which is that the middle 2 cards both have the letter N on them. I'm going to define my event. Let's call it B. So our middle 2 cards have the letters NN. So again, slots 2, 3, 4, 5, 6. So we have these 6 slots, and the middle 2 should contain NN. So we've placed those. That's it. What we need to do now is to arrange the other letters around those. So we have L, O, D, O that need to go into those slots. So just a number of ways then of arranging the LODO. And that would be 4 letters, 4 objects. 2 of them are alike. So 12, which means the probability that the middle 2 cards have NN would be 12 divided by our 180. 1/15. C says, find the probability that the 2 cards with letter O are adjacent and the 2 cards with letter N are also adjacent. And adjacent here means together, beside each other. So we're looking for the 2 cards with letter O to be together and the 2 cards with letter N to be together. So we have L, and then we want OO. I'm missing D. All right, so basically, just like the question we worked with the 10 students, we want to keep these 2 O's and treat them as one object. We want to keep these 2 N's and treat them as one object, right? So we want to treat O's as one object and N's as one object, right? Which means we are arranging 4 objects. 1, 2, 3, 4. And that would be 4 4 factorial because we're treating this as 1, treating this as 1. We have a single L, a single D, so we're not dividing by anything. So it's just 4 factorial. And then, unlike with the 10 students, let's go back to that question. We had an additional piece here of arranging those two youngest between themselves. But we don't have that in this case because the two O's that we are treating as one object are indistinguishable. So are the two N's. They're indistinguishable. Unlike those two students that were clearly different, OO, you can't tell the difference between the two O's, and N, you can't tell the difference between the two N's. So we don't need this piece. We don't have to do this part of it. All right. So it's just now working out the probability. Let me define my C. Which is keeping the O's adjacent and the N's adjacent. And so the probability of C would be equal to 4 factorial, which is the number of ways of arranging these 4 objects, divided by the number in our sample space, which we had worked out to be 180. Which gives 2 out of 15. D, oh, this should actually be one question. There we go. D, the cards are shuffled again and placed in a line face down. The first 2 cards in the line are turned over and reveal the letters L and O. Find the probability that when the other 4 cards are turned over, the letters will spell London. So the cards were shuffled again. They were placed face down. First 2 cards are turned over and we see the letters L and O. What that is telling us is that we are working with a conditional probability question. We were given some information. It's not just 6 cards shuffled and we know nothing about the outcome. We know for a fact that the first 2 letters are L and O. Right? We know for a fact that those are the 2 letters, L and then O. So that's a given situation. Remember when we did conditional probability before and we talked about a given situation? What it means is that we can reduce the number in our sample space. So instead of our answer being out of 180, we can reduce the number in the sample space based on the number of arrangements of this. Right? How many of these would we have? Right? How many arrangements where we have the first letter being L and the second letter being O? How many of those? Well, for these 4 slots, we have N left, D, O, N, right? So we need to work out for our sample space, for our reduced sample space, instead of it being the 180 that we had gotten, it would simply be the number of ways of arranging NDON. Placing the L and the O, that's a given. So just arranging NDON, that's 4 factorial over 2 factorial. 4 letters, 2 N's, which is 12. Right? So that's our reduced sample space. So now our answer is going to be out of 12. Looking at the event though, let's go back to the event. Letters will spell London. So let's define that as D Well, the number in D would be 1 because we have the LO and we want to place NDON. One way of placing NDON in the other 4 slots, which means the probability that our letters will spell London is going to be 1 out of 12.